Thank you very much. All right, this is another lecture for 5 SSD0 Bayesian Machine Learning and Information Processing. This is the third probabilistic programming session. We are in a new lockdown, which is causing some trouble. I have a little daughter who is at home and is currently sick. So I'd like to keep this lecture as short as possible, actually. So this is the question and answer houring for Probabilistic Programming 3, Regression and Classification. I'll quickly go over the notebook and just highlight some points. If you could just all post your questions, then I'll answer them. When I'm done with Probabilistic Programming 3, I'll discuss the correct answers for the Probabilistic Programming 2 assignment, and then I'll introduce the assignment for Probabilistic Programming 3. Right, so Probabilistic Programming 3, Regression and Classification. So I presented you with two problem settings. They're sort of idealized situations. They're stories to help you understand some of the concepts that come by. I can imagine that you're all familiar with the basics of regression and classification, but this is of course in a Bayesian light. So Bayesian linear regression and Bayesian logistic regression. So the linear regression aspect is relatively straightforward. We have a data set of stock market levels gathered over a certain period in time, and we'd like to know whether the trend in the stock market is positive or negative over that period. So in the videos I discuss this model specification aspect, and then I'll show you how to convert the generative model into a Forney-style vector graph with which we can perform inference automatically. I think this is a good time to also mention that some of the code you've seen here is specific to Fornylab and specific to Julia, but the machine learning community is converging on a common and a convention for specifying models. So that's what probabilistic programming is. It's a general framework for specifying probabilistic models, and there are a variety of toolboxes that automate inference under the hood. Fornylab is just one of them. Every programming language has one. There's two basically flavors of automatic inference. One is called Monte Carlo sampling. The other one is called variational inference. Fornylab is more on the latter aspect, variational inference, but we'll discuss that later. Bert has a lecture on variational Bayes a bit later. Yes, so just to say that although some of the aspects here are specific to Fornylab and Julia, they do transfer from Julia and Fornylab to other languages and other software toolboxes. All of the principles that we teach you are valid all over the machine learning community. Right, so for regression, I've shown you two ways to do inference with Fornylab. One is a batch estimator, where we basically copy the likelihood part of the graph as many times as we have the number of samples, and we get a very accurate estimate out of that. So the prior changes from being widely distributed over this particular region of parameter space into something that's very sharply peaked in parameter space. Just to show you that it's you don't always have to do a batch estimate. Bayesian inference is also really suited for dynamical systems inference. And so we also have a recursive estimator where you would create just the subgraph for a single observation, and then after each, you start with the prior, then you make an observation, then you update your posterior. Your posterior becomes the prior for the next sample, and then you go through the entire data set. And that gives you, that's much faster in terms of inference, and it gives you a slightly worse posterior estimate. The credit assignment problem is a problem on discriminative classification. So you'll need the discriminative classification lecture by Bert. Bert treats the Laplace approximation in depth in his lectures, and I think that's one of the approximations that's easiest to understand from a mathematical point of view. So in Formulab, we have a different convention for treating logistic regression. So we specifically have this logit node, and this logit node does a form of local variational inference. And there's a reference to that in Bishop, but we don't go into detail on this mathematically. All you need to know here is that there's a logit node, and that implements that combination of a sigmoid function and a Bernoulli likelihood. Yeah, so that allows you to train the model, and then we make some predictions on this credit assignment problem, and that shows quite poor accuracy. So you might not like to leave mortgage assignment and small business loan assignments to a machine. All right, so that's the probabilistic programming session on regression and classification. Yes, so please just post your questions in chat if you have any. I will now move on to the second probabilistic programming assignment, the correct answers. So in this PP2 assignment, you were given this graph, which resembles one of the graphs from the exercises on factor graphs.
Sorry, are you sharing your screen? Because I can't see your screen.
Ah, right, yeah. That's, yeah. Thanks for reminding me. Yeah, that's, I was going through my screen, yeah. All right, I'll quickly recap a bit. Yeah, so regression classification, what I was saying is that, yeah, so we have this model specification part, and then we generate this huge graph when we want to get a batch estimate. You don't necessarily have to do it that way. You can also do this recursively, and then you just iterate this part of the graph over the data set, and that'll give you a nearly as accurate. Your posterior estimate will be nearly as accurate as with the batch estimate. And then with this credit assignment problem, we have this logit node, which implements this sigmoid and Bernoulli combination. Yeah, and the final test accuracy is 63%. Yeah, thanks for reminding me. I think your mic is still on. It's generating a bit of white noise. Yeah, so the PP2 assignment, yeah, we're given this graph. It resembles the one from the exercise. As I mentioned, on the left here, we have x and y, the two Gaussian random variables. Then we have a square node with a plus operation. So we add those two variables. That produces the temporary variable chi1. In the first question, you're asked, what are the parameters of the message going out of the left square node? So this node sends a message towards this variable chi1, which is the addition of the random variable x and the random variable y. So all of the questions in the second probabilistic programming assignment can be solved mathematically, but we want to do it automatically using Formulab. So you're given a few hints on this assignment. Your job is to add the two Gaussian random variables x and y and the resulting variable chi1 to the factor graph. You don't need to assign IDs, you don't need placeholders, you don't have to specify posterior factorization. All you have to do is add those variables as mentioned, and the rest of the code will compile everything for you. So as mentioned in the hints, we have an @random variable macro, so that's also what you have to use. And then you can say there's a variable which is distributed according to some distributions, either Gaussian mean variance, Gaussian mean precision, or any of the other distributions we've discussed so far. So you have x and y, and both are distributed as a Gaussian mean variance. The parameters for both were already given, so you just plug those in, mu of x and sigma of x. And then you add another random variable, chi1, which is the addition of x and y. Yeah, that's supposed to be. The algorithm, the rest of the code will just compile the algorithm for you, and it will spit out a message with a Gaussian message with mean 1, 1, and then a covariance matrix with 3, 0, 0, 2. And so the hidden tests in this block test your mean against the factor 1, 1, and test your covariance matrix to the matrix 3, 0, 0, 2. Right, so the second question is that suppose we have a Gaussian distributed random variable chi1, and we have this clamped transition matrix A, or this clamped matrix A. This one's 2 by 2, that's a 2 by 1 variable, and we now perform a multiplication. So chi2 is A times chi1. Similar as before, the part where you would add variables, we add a random variable chi1, which is Gaussian distributed with mean and variance. And then the parameters are already given, so you just plug those in, and then you add another variable. Chi2 is A times chi1. A is already given as well. So this produces a message 2, 1, and then 4, 0, 0, 1. And again, there's two cells that test your answers, the mean and covariance matrix. In the third part, the third question, we're moving on to this third, or this the rightmost part of this factor graph. We have a temporary variable chi2, which is Gaussian distributed. Then we have a vector b, and we say that z is chi2 minus b. And so can we compute a message going towards this variable z? Right, so this is very much the same as before. We add a chi2 variable, which is Gaussian distributed with mean and variance. Parameters are given, b is given, and yeah, we just add a random vector. Z is chi2 minus b. So your outgoing message is is a Gaussian message with mean 1, 0, and then an identity covariance matrix. And in this last block, it tests both of those. In total, you can get 5 points for this assignment. Yeah, and I will download the submissions after this lecture, and then I'll grade them. So Hannah asks, where can we find the somewhat complete documentation on Fornilab? That's a very good question. So Fornilab, well, okay, so this is going too fast. We have if you go to the website for the course, so bmlip.nl, this takes you to a subpage of our labs website. We're Bias Lab actually. And so here we have a button on top called software. So you go to fornilab.jl, and then you are automatically taken to the documentation page for Fornilab, and then there's a library user API, which shows all of the components. I have not pointed you here because Fornilab is actually quite large and contains a lot of things that we won't need throughout the course. But yeah, if you want to read up more on it, then that's there you can find it over there. Right, so this concludes the Probabilistic Programming 2, the assignment. Yeah, so I will download all of the submissions and then I'll start auto-grading. I hope to have this done by the end of the week. Again, there might be delays because yeah, with the lockdown, this is going to reduce productivity. So as of 3:30, the assignment for Probabilistic Programming 3 is available on Canvas. Oh, so assignments. So Probabilistic Programming 3 has been made available. It's in this assignment for regression and classification. You are going to compute the posterior predictive distribution for a regression model. So the first part of this assignment generates a particular data set. So this isn't a real life scenario or anything. This is just a synthetic data set. Then this second part generates a model and a message passing algorithm, and it actually computes. Oh yeah, so this part actually computes posteriors for each of the parameters. So now we have a trained model with Formulab, and we would like to do a forecast. So in this case, the input variable is the number of days, so we can extend that into the future and then compute what the regression function would look like, t plus something in the future. So Bert, in his lecture, talks extensively about this predictive distribution. There's a lot of material on this as well that we point to, for instance, Bishop, and in the Probabilistic Programming session, there's also a link towards Bishop and Bert's notes. So what your job is at this point, so we're looking, the notation that Bert uses for this predictive distribution is this X bullet for new samples. This is a regression problem over time, so consider this X bullet to be future time points. And then Y bullet is the prediction for those future time points. And so we've had a few discussions already in one of Bert's previous lectures on that you would just produce the mean estimate. But that's not super informative. And the main benefit of having of doing Bayesian inference is that you can quantify your uncertainty about this prediction, right? So if you want to forecast the weather, then you can not only say, well, I think tomorrow will be 19 degrees, but you can also say with what probability it might become 20 degrees or 18 degrees or something like that. And so in this first part of this assignment, so the first question, you're just going to compute the mean of the predictive distribution. So we define a variable X bullet, that's the future time steps. And then you're going to compute the mean for the predictive distribution. So that'll be mean Y bullet. And then we're going to visualize that, and that should look something like this. So the figure that you see here is me generating that that mean Y bullet and then saving it as an image, and that's stored alongside the notebook. This isn't a variable that's available to you in the assignment. And as you can see, this forecast, just this line itself, is just not that informative. It doesn't tell you that much about where you expect the data to be. It's almost certainly not going to be on that line. So again, a few checks on your predictive distribution. And so in the second question, you will also compute the covariance of the predictive distribution. So spoiler, the predictive distribution is a Gaussian, so it's parameterized by mean and covariance matrix. And once you compute the covariance matrix, you can use that to visualize the uncertainty of your forecast, and that should look something like this. So you can imagine if suppose this was some weather information, then you can now say that with some uncertainty, it's going to be larger. It's going to be warmer or colder than your mean estimate. And that's actually it. So it's fairly straightforward this time, this assignment. Again, you can get 5 points on this. And the deadline for this is the next Probabilistic Programming session, which is the 13th of January. And again, it's at 3:30, not at 11:59. I don't see any questions on Probabilistic Programming 3. So if you still have anything, if there's something you didn't understand, then feel free to ask. Again, I think, well, I'm just going to keep talking for a minute to give you a chance to ask questions. I think most of you are familiar with regression and classification. You've all seen this before. I think, the main difficulty is in translating this into Bayesian terms. And I think Bert's done a great job on that theoretically. This implements the model that Bert talks about. It's fairly short, the model description syntax. And in the next probabilistic programming session, we'll be doing a latent variable model and a dynamic model, and they'll become a bit bigger, the model specifications in Formulab. They'll still be relatively short compared to for instance, TensorFlow, deep learning, a neural network specification. Yeah, so there was one question on Piazza about how to interpret these visualizations. The student answer was great. I think I couldn't have said it better myself. In hindsight, I realized that, so I wanted to clearly define or clearly show that one of them is the prior and one of them is the posterior. So I used red and blue. But the question on Piazza, at least I noticed from the question on Piazza that it might be hard to interpret this visualization now that you've lost this color map. Yeah, so my only point for this was that the peak, so the color map here, the top part, that's the peak of the distribution, which is roughly here. And then this thing just falls down from there. This peak has a probability of 0.16, and then this peak has a probability of 300, and that's just orders of magnitude larger. And that's, I think, the only takeaway message from these plots. All right. If there aren't any other questions, then I'm going to stop this session already. Maybe just as a double check, are people lagging behind? If you've managed to watch the probabilistic programming sessions and have completed the assignment, could you just post yes in chat? That'll give us an idea of whether you're actually up to speed or whether you're lagging behind and haven't had the time for it yet. That's 4 answers. Very well done. Well done. It's a demanding course. I hope Bert's summary lecture has been helpful. Although I think that you should take the time off during Christmas break to rest up a bit. But I hope that also gives you some time for all of this material to settle and yeah. All right. 6 is still not a lot, but so we'll have another check after this, I think, after the Christmas break. All right. If there are no further questions, then I'm going to stop the session here. We'll see you all on Friday, I think.